Let's start today's video with the blocking versus non-blocking. So, before understanding blocking and non-blocking assignments, we need to understand where they are used. In Verilog, sequential behavior is described using the procedural blocks, like always blocks and initial block. Inside these procedural blocks, we can assign values to variable using two different assignment types. The first one is blocking assignment, represent using equal to sign. The second one is non-blocking assignment, represented using less than equal symbol. These two assignments may look similar, but they behave very differently during simulation and hardware synthesis. In this video, we will understand how each assignment works, how hardware is implemented, and why mixing them incorrectly can cause serious RTL bugs. So let's first understand blocking assignment. Blocking assignments use the equal sign operator. The key idea is that blocking assignments execute sequentially. This means the simulator executes one statement at a time and wait for that statement to complete before moving to the next statement. Let's look at the example. Inside the combinational always block, we assign A equal to B and then C equal to A. During the simulation, the first line executes and A immediately gets the value of B. Then the second line executes and C receives the updated value of A. Since A already become B, C also become B. So in this case, the final result is that both A and C become equal to B. Now let's see what hardware this code represent. Because this always block is sensitive to all signals and describes the combinational logic, the synthesis tool interpret this as simple combinational connection. The first statement connects the signal B to A. The second statement assigns C equal to A. But since A already receives B, effectively C also becomes equal to B. So in hardware, both A and C are directly driven by signal B. This means no flip-flop or storage elements are created. This is just simple combinational logic. Now let's understand non-blocking assignments. Non-blocking assignments uses less than equal operator. They are mainly used for sequential logic, such as a flip-flop. Unlike blocking assignment, non-blocking assignments do not update variables immediately. Instead, the simulator first evaluates the right-hand side of the assignment, then updates are scheduled and applied simultaneously at the clock edge. Let's see this example. At the clock edge, the simulator first evaluates the right-hand side value. So it reads B and the current value of A. Then both registers update together. This means A receives value of B while C receives the previous value of A. Now let's see how this code translates to the hardware. Since the always block is triggered on the positive edge of the clock, the synthesis tool infers the flip-flops. The first assignment creates a flip-flop where A captures the value of B at every clock edge. The second assignment creates another flip-flop where C captures the value of A so the data flows from B to A, then from A to C. This creates a pipeline of two registers. At every clock edge, A receives B and C receives the previous value of A. This example shows why mixing blocking and non-blocking assignment can create serious RTL bug. Let's look at this code carefully. Inside a clocked always block, we first assign A equal to B using the blocking assignment. Because blocking assignments executes immediately, A gets updated value of B right away. Next, we have a non-blocking assignment where C is assigned the value of A, but since A was already updated in the previous line, C now receives B. So during simulation, both A and C appears to get value of B. However, synthesis tools do not follow the same execution model as a simulator. Instead, they interpret the code based on the hardware behavior. Since this block is triggered by the clock, the synthesis tool creates two flip-flops. The first flip-flop stores the value of B into A. The second flip-flop stores the value of A into C. This means in the real hardware, C actually receives the previous value of A, not B. So simulation results become different from the actual hardware behavior. This difference between simulation and hardware is called the simulation synthesis mismatch. To avoid this issue, RTL Designer follow a simple rule: blocking assignments should be used for the combinational logic and non-blocking assignments should be used for the sequential logic, such as a flip-flop. Following this guideline ensure that simulation behavior matches hardware implementation.